A linear regression is one of the easiest algorithms in machine learning. It is a statistical model that attempts to show the relationship between two variables with a linear equation. Hello everyone, this is Atul from Edureka, and in today's session we'll learn about linear regression algorithm. But before we drill down to linear regression algorithm in depth, I'll give you a quick overview of today's agenda. So we'll start our session with a quick overview of what is regression, as linear regression is one of a type of regression algorithm. Once we learn about regression, its use case, the various types of it, next we'll learn about the algorithm from scratch, where I'll teach you its mathematical implementation first. Then we'll drill down to the coding part and implement linear regression using Python. In today's session, we'll deal with linear regression algorithm using least square method, check its goodness of fit or how close the data is to the fitted regression line using the R-square method. And then finally, what we'll do, we'll optimize it using the gradient descent method. In the last part, on the coding session, I'll teach you to implement linear regression using Python. And the coding session would be divided into two parts. The first part would consist of linear regression using Python from scratch, where you will use the mathematical algorithm that you have learned in this session. And in the next part of the coding session, we'll be using scikit-learn for direct implementation of linear regression. Alright, I hope the agenda is clear to you guys. Alright, so let's begin our session with what is regression? Well, regression analysis is a form of predictive modeling technique which investigates the relationship between a dependent and independent variable. A regression analysis involves graphing a line over a set of data points that most closely fits the overall shape of the data. A regression shows the changes in a dependent variable on the y-axis to the changes in the explanatory variable on the x-axis. Fine. Now you'd ask, what are the uses of regression? Well, there are major three uses of regression analysis. The first being determining the strength of predicators. The regression might be used to identify the strength of the effect that the independent variables have on the dependent variable. For example, you can ask question like, what is the strength of relationship between sales and marketing spending? Or what is the relationship between age and income? Second is forecasting an effect. In this, the regression can be used to forecast effects or impact of changes. That is, the regression analysis help us to understand how much the dependent variable changes with the change in one or more independent variable. Fine. For example, you can ask question like, how much additional sale income will I get for each $1,000 spent on marketing? Third is trend forecasting. In this, the regression analysis predict trends and future values. The regression analysis can be used to get point estimates. In this, you can ask questions like, what will be the price of Bitcoin in next 6 months, right? So next topic is linear versus logistic regression. By now, I hope that you know what a regression is. So let's move on and understand its type. So there are various kinds of regression like linear regression, logistic regression, polynomial regression, and others. All right. But for this session, we'll be focusing on linear and logistic regression. So let's move on and let me tell you what is linear regression and what is logistic regression. Then what we'll do, we'll compare both of them. All right. So starting with linear regression. In simple linear regression, we are interested in things like y equal mx plus c. So what we are trying to find is the correlation between x and y variable. This means that every value of x has a corresponding value of y in it if it is continuous. Alright? However, in logistic regression, we are not fitting our data to a straight line like linear regression. Instead, what we are doing, we are mapping y versus x to a sigmoid function. In logistic regression, what we find out is y 1 or 0 for this particular value of x. So thus we are essentially deciding true or false value for a given value of x. Fine. So as a core concept of linear regression, you can say that the data is modeled using a straight line, where in the case of logistic regression, the data is modeled using a sigmoid function. The linear regression is used with continuous variables. On the other hand, the logistic regression, it is used with categorical variable. The output or the prediction of a linear regression is the value of the variable. On the other hand, the output or prediction of a logistic regression is the probability of occurrence of the event. Now, how will you check the accuracy and goodness of fit? In case of linear regression, you have various methods like measured by loss, R squared, adjusted R squared, etc. While in the case of logistic regression, you have accuracy, precision, recall, F1 score, which is nothing but the harmonic mean of precision and recall. Next is ROC curve for determining the probability threshold for classification or the confusion matrix, etc. There are many. All right. So summarizing the difference between linear and logistic regression, you can say that the type of function you are mapping to is the main point of difference between linear and logistic regression. A linear regression maps a continuous x to a continuous y. On the other hand, a logistic regression maps a continuous x to the binary y. So we can use logistic regression to make category or true-false decisions from the data. Fine, so let's move on ahead. Next is linear regression selection criteria, or you can say when will you use linear regression. So the first is classification and regression capabilities. Regression models predict a continuous variable, such as the sales made on a day, or predict the temperature of a city. Their reliance on a polynomial like a straight line to fit a data set poses a real challenge when it comes towards building a classification capability. Let's imagine that you fit a line with the training points that you have. Now imagine you add some more data points to it. But in order to fit it, what do you have to do? You have to change your existing model. That is, maybe you have to change the threshold itself. So this will happen with each new data point you add to the model. Hence, the linear regression is not good for classification models. Fine. Next is data quality. Each missing value removes one data point that could optimize the regression. In simple linear regression, the outliers can significantly disrupt the outcome. Just for now, you can know that if you remove the outliers, your model will become very good. All right. So this is about data quality. Next is computational complexity. The linear regression is often not computationally expensive as compared to the decision tree or the clustering algorithm. The order of complexity for n training example and x features usually falls in either big O of x square or big O of xn. Next is comprehensible and transparent. The linear regression are easily comprehensible and transparent in nature. They can be represented by a simpler mathematical notation to anyone and can be understood very easily. So these are some of the criteria based on which you'll select the linear regression algorithm. Alright, next is where is linear regression used? First is evaluating trends and sales estimate. Well, linear regression can be used in business to evaluate trends and make estimates or forecasts. For example, if a company's sales have increased steadily every month for past few years, then conducting a linear analysis on the sales data with monthly sales on the y-axis and time on the x-axis. This will give you a line that predicts the upward trends in the sale. After creating the trend line, the company could use the slope of the lines to forecast sale in future months. Next is analyzing the impact of price changes. Well, linear regression can be used to analyze the effect of pricing on consumer behavior. For instance, if a company changes the price on a certain product several times, then it can record the quantity itself for each price level and then perform a linear regression with sold quantity as a dependent variable and price as the independent variable. This would result in a line that depicts the extent to which the customer reduced their consumption of the product as the price is increasing. So this result would help us in future pricing decisions. Next is assessment of risk in financial services and insurance domain. Well, linear regression can be used to analyze the risk. For example, a health insurance company might conduct a linear regression algorithm. How it can do? It can do it by plotting the number of claims per customer against its age. And they might discover that the old customers tend to make more health insurance claim. Well, the result of such an analysis might guide important business decisions. All right. So by now you have just a rough idea of what linear regression algorithm is, like what it does, where it is used, when you should use it. All right. Now let's move on and understand the algorithm in depth. So suppose you have independent variable on the x-axis and dependent variable on the y-axis. All right. Suppose this is the data point on the x-axis. The independent variable is increasing on the x-axis, and so does the dependent variable on the y-axis. So what kind of linear regression line you would get? You'd get a positive linear regression line. All right, as the slope would be positive. Next is, suppose you have an independent variable on the x-axis, which is increasing. And on the other hand, the dependent variable on the y-axis, that is decreasing. So what kind of line will you get in that case? You'll get a negative regression line in this case, as the slope of the line is negative. And this particular line, that is line of y equal mx plus c, is a line of linear regression, which shows the relationship between independent variable and dependent variable. And this line is only known as line of linear regression. Okay. So let's add some data points to our graph. So these are some observation or data points on our graphs. Let's plot some more. Okay. Now all our data points are plotted. Now our task is to create a regression line or the best fit line. All right. Now once our regression line is drawn, now it's the task of prediction. Now suppose this is our estimated value or the predicted value, and this is our actual value. Okay, so what we have to do, our main goal is to reduce this error, that is to reduce the distance between the estimated or the predicted value and the actual value. The best fit line would be the one which had the least error or the least difference in estimated value and the actual value. All right. In other words, we have to minimize the error. This was a brief understanding of linear regression algorithm. Soon we'll jump to its mathematical implementation. All right. But for then, let me tell you this. Suppose you draw a graph with speed on the x-axis and distance covered on the y-axis with the time remaining constant. If you plot a graph between the speed traveled by the vehicle and the distance traveled in a fixed unit of time, then you will get a positive relationship. All right. So suppose the equation of line is y equal mx plus c. Then in this case, y is the distance traveled in a fixed duration of time. X is the speed of vehicle, m is the positive slope of the line, and c is the y-intercept of the line. All right. Suppose the distance remaining constant, you have to plot a graph between the speed of the vehicle and the time taken to travel a fixed distance. Then in that case, you'll get a line with a negative relationship. All right, the slope of the line is negative. Here the equation of line changes to y equal minus of mx plus c, where y is the time taken to travel a fixed distance, x is the speed of vehicle, m is the negative slope of the line, and c is the y-intercept of the line. All right. Now let's get back to our independent and dependent variable. So in that term, y is our dependent variable and x, that is our independent variable. Now let's move on and see the mathematical implementation of the things. All right. So we have x equal 1, 2, 3, 4, 5. Let's plot them on the x-axis. So 0, 1, 2, 3, 4, 5, 6. All right. And we have y as 3, 4, 2, 4, 5. All right. So let's plot 1, 2, 3, 4, 5 on the y-axis. Now let's plot our coordinates one by one. So x equal 1 and y equal 3. So we have here x equal 1 and y equal 3. So this is our point 1, 3. So similarly, we have 1, 3, 2, 4, 3, 2, 4, 4, and 5, 5. All right. So moving on ahead, let's calculate the mean of x and y and plot it on the graph. All right. So mean of x is 1 plus 2 plus 3 plus 4 plus 5 divided by 5, that is 3. All right. Similarly, mean of y is 3 plus 4 plus 2 plus 4 plus 5, that is 18. So 18 divided by 5, that is nothing but 3.6. All right. So next what we'll do, we'll plot our mean, that is 3, 3.6 on the graph. Okay. So there's a point 3, 3.6. See, our goal is to find or predict the best fit line using the least square method. All right. So in order to find that, we first need to find the equation of line. So let's find the equation of our regression line. All right. So let's suppose this is our regression line y equal mx plus c. Now we have an equation of line. So all we need to do is find the value of m and c, where m equals summation of x minus x bar multiplied by y minus y bar upon the summation of x minus x bar whole square. Don't get confused. Let me resolve it for you. All right. So moving on ahead, as a part of formula, what we are going to do, we'll calculate x minus x bar. So we have x as 1 minus x bar as 3. So 1 minus 3, that is minus 2. Next we have x equal 2 minus its mean 3, that is minus 1. Similarly, we have 3 minus 3 is 0, 4 minus 3 1, 5 minus 3 2. All right. So x minus x bar, it's nothing but the distance of all the point through the line y equal 3. And what does this y minus y bar implies? It implies the distance of all the point from the line x equal 3.6. Fine. So let's calculate the value of y minus y bar. So starting with y equal 3 minus value of y bar, that is 3.6. So it is 3 minus 3.6. How much? Minus of 0.6. Next is 4 minus 3.6. That is 0.4. Next 2 minus 3.6. That is minus of 1.6. Next is 4 minus 3.6. That is 0.4. Again 5 minus 3.6. That is 1.4. All right. So now we are done with y minus y bar. Fine. Now next we'll calculate x minus x bar whole square. So let's calculate x minus x bar whole square. So it is minus 2 whole square, that is 4, minus 1 whole square, that is 1, 0 square 0, 1 square 1, 2 square 4. Fine. So now in our table we have x minus x bar, y minus y bar, and x minus x bar whole square. Now what we need the product of x minus x bar multiplied by y minus y bar. Alright, so let's see the product of x minus x bar multiplied by y minus y bar. That is minus of 2 multiplied by minus of 0.6, that is 1.2. Minus of 1 multiplied by 0.4, that is minus of 0.4. 0 multiplied by minus of 1.6, that is 0. 1 multiplied by 0.4, that is 0.4. And next 2 multiplied by 1.4, that is 2.8. Alright, now almost all the parts of our formula is done. So now what we need to do is get the summation of last two columns. Alright, so the summation of x minus x bar whole square is 10, and the summation of x minus x bar multiplied by y minus y bar is 4. So the value of m will be equal to 4 by 10. Fine. So let's put this value of m equals 0.4 in our line y equal mx plus c. So let's fill all the points into the equation and find the value of c. So we have y as 3.6. Remember the mean y? M as 0.4, which we calculated just now. X as the mean value of x, that is 3. And we have the equation as 3.6 equals 0.4 multiplied by 3 plus c. Alright, that is 3.6 equal 1.2 plus c. So what is the value of c? That is 3.6 minus 1.2, that is 2.4. Alright, so what we had m equals 0.4, c as 2.4, and then finally when we calculate the equation of regression line, what we get is y equal 0.4 times of x plus 2.4. So this is the regression line. Alright, so this is how you're plotting your points. This is your actual point. Alright, now for given m equals 0.4 and c equal 2.4, let's predict the value of y for x equal 1, 2, 3, 4 and 5. So when x equal 1, the predicted value of y will be 0.4 multiplied by 1 plus 2.4, that is 2.8. Similarly, when x equal 2, predicted value of y will be 0.4 multiplied by 2 plus 2.4, that equals to 3.2. Similarly, x equal 3, y will be 3.6. X equal 4, y will be 4.0. X equal 5, y will be 4.4. So let's plot them on the graph, and the line passing through all these predicting points and cutting y-axis at 2.4 is the line of regression. Now your task is to calculate the distance between the actual and the predicted value, and your job is to reduce the distance. Alright? Or in other words, you have to reduce the error between the actual and the predicted value. The line with the least error will be the line of linear regression or regression line, and it will also be the best fit line. Alright? So this is how things work in computer. So what it performs n number of iteration for different values of m. For different values of m, it will calculate the equation of line where y equal mx plus c, right? So as the value of m changes, the line is changing. So iteration will start from 1, alright, and it will perform n number of iteration. So after every iteration, what it will do, it will calculate the predicted value according to the line and compare the distance of actual value to the predicted value. And the value of m for which the distance between the actual and the predicted value is minimum will be selected as the best fit line. Alright. Now that we have calculated the best fit line, now it's time to check the goodness of fit or to check how good a model is performing. So in order to do that, we have a method called R-square method. So what is this R-square? Well, R-squared value is a statistical measure of how close the data are to the fitted regression line. In general, it is considered that a high R-squared value model is a good model. But you can also have a low R-squared value for a good model as well, or a high R-squared value for a model that does not fit at all. Alright. It is also known as coefficient of determination or the coefficient of multiple determination. Let's move on and see how R-square is calculated. So these are our actual values plotted on the graph. We had calculated the predicted values of y as 2.8, 3.2, 3.6, 4.0, 4.4. Remember when we calculated the predicted values of y for the equation y predicted equals 0.4 times of x plus 2.4 for every x equal 1, 2, 3, 4 and 5. From there we got the predicted values of y. Alright. So let's plot it on the graph. So these are a point and the line passing through these points are nothing but the regression line. Alright. Now what you need to do is you have to check and compare the distance of actual minus mean versus the distance of predicted minus mean. Alright. So basically what you're doing, you're calculating the distance of actual value to the mean to distance of predicted value to the mean. Alright. So there's nothing but R square. In mathematically, you can represent r square as summation of y predicted values minus y bar whole square divided by summation of y minus y bar whole square, where y is the actual value, yp is the predicted value, and y bar is the mean value of y. That is nothing but 3.6. So remember, this is our formula. So next what we'll do, we'll calculate y minus y bar. So we have y as 3, y bar as 3.6. So we'll calculate it as 3 minus 3.6, that is nothing but minus of 0.6. Similarly, for y equal 4 and y bar equal 3.6, we have y minus y bar as 0.4. Then 2 minus 3.6, it is 1.6. 4 minus 3.6, again 0.4. And 5 minus 3.6, it is 1.4. So we got the value of y minus y bar. Now what we have to do, we have to take it square. So we have minus of 0.6 square as 0.36, 0.4 square as 0.16, minus of 1.6 square as 2.56, 0.4 square as 0.16, and 1.4 square as 1.96. Now as a part of formula, what we need our yp minus y bar value. So these are yp values and we have to subtract it from the mean of y. So 2.8 minus 3.6, that is minus 0.8. Similarly, we'll get 3.2 minus 3.6, that is 0.4. And 3.6 minus 3.6, that is 0. 4.0 minus 3.6, that is 0.4. Then 4.4 minus 3.6, that is 0.8. So we calculated the value of yp minus y bar. Now it's our turn to calculate the value of yp minus y bar whole square. Next we have minus of 0.8 square as 0.64, minus of 0.4 square as 0.16, 0 square 0, 0.4 square as again 0.16, and 0.8 square as 0.64. Alright. Now as a part of formula, what it suggests me to take the summation of yp minus y bar whole square and summation of y minus y bar whole square. Alright, let's see. So on summating y minus y bar whole square, what you get is 5.2. And summation of yp minus y bar whole square, you get 1.6. So the value of r square can be calculated as 1.6 upon 5.2. Fine. So the result which you'll get is approximately equal to 0.3. Well, this is not a good fit. Alright. So it suggests that the data points are far away from the regression line. Alright. So this is how your graph will look like when r square is 0.3. When you increase the value of r square to 0.7, so you'll see that the actual value would lie closer to the regression line. When it reaches to 0.9, it comes more close. And when the value approximately equals to 1, then the actual values lies on the regression line itself. For example, in this case, if you get a very low value of r square, suppose 0.02, so in that case, what you'll see that the actual values are very far away from the regression line. Or you can say that there are too many outliers in your data. You cannot forecast anything from the data. All right. So this was all about the calculation of r square. Now you might get a question like, are low values of r square always bad? Well, in some field, it is entirely expected that our r square value will be low. For example, any field that attempts to predict human behavior, such as psychology, typically has r squared values lower than around 50%, through which you can conclude that humans are simply harder to predict than the physical process. Furthermore, if your r squared value is low, but you have statistically significant predicators, then you can still draw important conclusion about how changes in the predicator values are associated with the changes in the response value. Regardless of the r squared, the significant coefficient still represent the mean change in the response for 1 unit of change in the predicator, while holding other predicators in the model constant. Obviously, this type of information can be extremely valuable. Alright? Alright, so this was all about the theoretical concept. Now let's move on to the coding part and understand the code in depth. So for implementing linear regression using Python, I'll be using Anaconda with Jupyter Notebook installed on it. So alright, this is our Jupyter Notebook and we are using Python 3.0 on it. Alright. So we are going to use a data set consisting of head size and human brain of different people. Alright. So let's import our data set. %matplotlib inline. We are importing numpy as np, pandas as pd, and matplotlib. And from matplotlib, we are importing pyplot of that as plt. Alright. Next, we'll import our data headbrain.csv and store it in the data variable. Let's execute the run button and see the output. So this asterisk symbol, it symbolizes that it's still executing. So there's our output. Our data set consists of 237 rows and 4 columns. We have columns as gender, age range, head size in centimeter cube, and brain weights in gram. Fine. So this is our sample data set. This is how it looks. It consists of all these data set. So now that we have imported our data, so as you can see, there are 237 values in the training set. So we can find a linear relationship between the head size and the brain weights. So now what we'll do, we'll collect X and Y. The X would consist of the head size values and the Y would consist of brain weight values. So collecting X and Y, let's execute the run. Done. Next, what we'll do, we need to find the values of B1 or B0, or you can say M and C. So we'll need the mean of X and Y values. First of all, what we'll do, we'll calculate the mean of X and Y. So mean X equal NP dot mean X. So mean is a predefined function of numpy. Similarly, mean underscore Y equal NP dot mean of Y. So what it will return? It will return the mean values of Y. Next, we'll check the total number of values. So M equal length of X. All right. Then we'll use the formula to calculate the values of B1 and B0 or M and C. All right, let's execute the run button and see what is the result. So as you can see here on the screen, we have got B1 as 0.263 and B0 as 325.57. All right. So now that we have our coefficient, so comparing it with the equation y equal mx plus c, you can say that brain weight equals 0.263 multiplied by head size plus 325.57. So you can say that the value of m here is 0.263 and the value of c here is 325.57. All right. So this is our linear model. Now let's plot it and see graphically. Let's execute it. So this is how our plot looks like. This model is not so bad, but we need to find out how good our model is. So in order to find it, there are many methods like root mean square method, the coefficient or determination, or the R-square method. So in this tutorial, I have told you about R-square method. So let's focus on that and see how good our model is. So let's calculate the R-square value. All right. Here SS underscore T is the total sum of square. SS underscore R is the total sum of square of residuals. And R square as per formula is 1 minus total sum of squares upon total sum of square of residuals. Alright. Next, when you execute it, you'll get the value of R square as 0.63, which is pretty very good. Now that you have implemented simple linear regression model using least square method, let's move on and see how will you implement the model using machine learning library called scikit-learn. Alright. So this scikit-learn is a simple machine learning library in Python. Building machine learning model are very easy using scikit-learn. So suppose there's your Python code. So using the scikit-learn libraries, your code shortens to this length. All right. So let's execute the run button and see. You'll get the same R2 score as. Well, this was all for today's discussion. In case you have any doubt, feel free to add your query to the comment section. Thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!